Welcome everyone. I'm very happy to introduce you this new series of GIF talks with the industry series. This is a webinar that we are promoting, aiming at supporting the LFR development. And today we have the pleasure to host newcleo in the person of Francisco Garcia Ferre, who will provide you an overview concerning the newcleo's material strategy for Generation 4 LFR research and development. Before starting, let me introduce myself. I am Mariano Tarantino, the Euratom representative of the GIF LFR Provisional System Steering Committee. And before starting, a few, let's say, remarks about this webinar. Because many people are connected today, we are expecting around 100 people to join for this webinar. And to assure a stability of the presentation, we have implemented the closure of your video and the audio function. But feel free to use the question and the answer function to provide your feedback, to provide your question. And at the end of the presentation of Francisco, we will be happy to answer your question. And also, please let us know if for any reason you have difficulties in hearing us or following the webinar. So still use the question and answer function to provide us any feedback. Let me stress also that this webinar will be recorded and then will be available on our website. Before moving on, let me introduce very shortly what is let's say the roles, the rule, and what we are doing for promoting Generation 4 LFR in the frame of the GIF community. As you may know, the GIF is supporting several, let's say, innovative systems. Among the other, we have LFR, but you see that other concepts are available. So the gas fast reactor, the molten salt reactor, sodium fast reactor, supercritical water reactor, and very high temperature reactor. But you know, the goal of this system is to increase sustainability and to promote the waste reduction in the nuclear application, to improve the economics, to improve safety and reliability, and to improve the resistance against the proliferation and the physical protection. So these are the common goals that are implemented in GIF systems. And as you can see from this slide, we are organizing in a well-structured teams. We have the Generation 4 International Forum, and below them we have several working group or task force that are implementing the goal of the program. Concerning the mission that we have in the last 20 years, it's worth to mention that we are promoting R&D on this Generation 4 system to advance technology, to support technology development. Some of these systems are already in the demonstration phase. And also, GIF case by case is adapting its format to support the collaboration and to promote the deployment of such systems. And according to that, one of the, let's say, the goal that we achieved starting from last year is the way to promote this technology development involving industries. So this is a way to underline that when industries are involved, the maturity is quite high. And so this is the reason why we are today promoting this kind of webinar. So moving quickly on the LFR reactor activities, we have several, let's say, activity ongoing worldwide. Moving quickly, we have a contribution from China. In China, there is a huge program ongoing, mostly in the frame of a clear series. And you see that they have several platforms already ongoing, like ClearM, ClearM for it's a project in which to develop a small modular transportable reactor with 10 megawatt electric. They are planning to work on Clear 400 or Clear-A, that is an EDS. And they have in place already the Nirvana platform for an engineering verification, and the ClearM0, that is an electrical simulator. And in parallel, there are also the other activities ongoing. It's worth to mention the Chinese accelerator-driven system led by Chinese Academy of Science. But also in Europe, we are doing several activities. We have several projects in parallel right now. We have the ALFRED project developed by the Falcon Consortium. We have CLR55 that is a Swedish LFR developed by Blekalla. Then we have the newcleo that are promoting the LFRs 30 or 200. And then we have MIRA from the Belgian colleague. And more recently, SEK is promoting also an SMR called by LFR. We will have time in the next webinar to deep analyze this project. In Japan, the Japanese colleagues are working mostly at Tokyo Institute of Technology or the Japan Atomic Energy Agency to promote the design of innovative LFR or to progress with the CFD analysis or let's say material testing, like for example the LBA corrosion study in a Logi loop. Moreover, we have the contribution from the Republic of Korea with the Micro-Ranos project. Micro-Ranos has already completed let's say the phase of the conceptual design, and they are working on the development of a lower enriched uranium core, developing a new kind of material that are resistant against the corrosion and radiation, like the AFA improved with the titanium. They are working on the demonstration of the safety of their system, developing a methodology and practice to analyze a severe accident. And also they are working quite a lot to demonstrate the integration of this kind of system with renewable source. In US, there are many activities ongoing, mostly, let's say, promoted by the Nuclear Energy University project, so by the university. It's worth to mention the activity at MIT, Massachusetts Institute of Technology, in which they are studying the synergetic effect of lead and irradiation with the ions, or the activity by the University of Pittsburgh, in which they are making a test for corrosion in flowing lead. Again, at Argonne, they are developing, sometimes in collaboration with the Westinghouse, also the development of numerical tools, or let's say a platform for numerical analysis that are very powerful in supporting the design and the safety analysis of such kind of system. Going to conclude, we have several activities that can you find on our website. Recently, we are working on the issues of a new version of the safety design criteria. The first issue was in March 2021, soon we'll have a new version of this document. But also we have delivered the white paper or the LFR system safety assessment in 2020 or 2021 respectively. More recently in Brasimone, we had also the GLANST workshop with the 45 participants, the 28 contribution with some invited speakers involving industries. And it was very successful because there we had the possibility to discuss the status of the LFR development worldwide. And soon the outcome, the book of abstract of this, let's say, symposium will be available on the website of the GIF. So I invite you to have a check on the website, because soon you can download the book of abstract and also the presentation with all the contents of our workshop. So let's move on. Let's start officially this LFR webinars in 2025. Now we are going to start with newcleo. This is the first one. Later on we'll have the presentation in July from Blekalla, in October from Ansaldo Nucleare. Let me introduce my colleague and friend Francisco Garcia Ferre. Francisco has a long experience in leading academic and industrial innovation. He has held a number of roles at the CA, Italian Institute of Technology in Italy, ABB, and now is moved in newcleo, and the newcleo is the global manager for the L&D research and development, the R&D on material for LFR. Francisco holds a Master of Science in Nuclear Energy and a PhD in Energy in the Nuclear Science and Technology, both from Polytechnic of Milan with honors. So I'm very happy to leave the floor to Francisco. Francisco, welcome to this webinar. The floor is yours, and we will be very happy to follow your presentation. Thank you.
Hey, Mariano, thank you very much, and good afternoon to everyone. Thanks for the nice introduction, Mariano, again. Big pleasure to be here. So thank you for the invitation. Thanks to the Generation IV International Forum. It's really an honor to be here and talk a little bit about what newcleo is doing. So I'll try to share my screen now. Please give me 1 second and I'll enter presentation mode. Do you confirm you're seeing the screen, Mariano, please, maybe?
We see the screen, but not in full. Yeah. Now we're seeing not in presentation mode. Yes, just swap it. Yeah, perfect. Go ahead.
Okay.
Perfect.
Fantastic. Okay, I have a small issue. Okay, much better now. Good, so you see the full screen, right?
Yes, it's okay.
Okay, thanks again, and thank you everyone for being here today. I'll be talking a little bit about the newcleo strategy for materials relative to Generation IV systems, but specifically the lead fast reactor systems that we are designing. Before that, I'll guide you through a little bit about what Nucleo Reality is. It's a new company. It's a new player in this field. Nucleo was launched in September 2021. So back then it really was a startup company, although by now we have become a relatively big organization with over 1,100 employees. So that's quite a thing to achieve in a couple of years, and it's been possible through a number of developments, and not the least the fundraising activity. So far we've raised over 530 million, and part of this financing that we have raised was utilized to do some merger and acquisition to acquire EPCM capability. So specifically Fucina, SRS, and Rucci are 3 companies that we acquired, 2 of which are based in Italy, Fucina and SRS, whereas Rucci is a French-Swiss company producing pumps for the nuclear field. And let's say these acquisitions also helped Nucleo achieve a turnover of 50 million in 2024. So very smart utilization of those funds that we managed to acquire. But yeah, what the mission of Nucleo is to essentially contribute to developing safe, clean, and sustainable nuclear energy. And the way we want to do it is twofold. And usually we talk a lot about our small modular reactor, but I always like to place above that the fact that we want to manufacture our own mixed oxide fuel. So the first thing we want to do is manufacture fuel, and this is with the intention of closing the nuclear fuel cycle. And the second thing that Nucleo wants to do is to design, deploy a fleet of small modular reactors that may utilize that fuel to achieve the closure of that nuclear fuel cycle. So I guess the audience is quite familiar with this concept, but just in case, a small refresher for everyone. The utilization of resources today when it comes to uranium is not a very efficient. 90% of natural uranium is considered waste, so we have the depleted uranium, that's the big chunk here, and only 10% is actually used to produce energy. But eventually we get only 0.5% of the energy contained in the natural uranium out for our own purposes, right? So what's left behind is some sort of waste, which could either be sent directly to storage, and that would entail that natural radioactivity levels are only repristined after many hundreds of thousands of years, or it could be reprocessed to extract some of the remnants of plutonium, uranium-235, and if utilized also with the depleted uranium and the uranium remaining in that waste initially, we could still produce a lot of energy, and that's what we intend to do specifically with fast reactors. So by applying this reprocessing and putting that reprocessed fuel into a fast reactor and eventually repeating this cycle, we could ultimately pursue this green curve over here, which would also require the utilization or the loading of the fuel with some minor actinides. So that's, let's say, a holy grail. But the main starting point as an intermediate step towards that is to start reprocessing the fuel systematically, and that's one of the goals that we would like to pursue. So that's thing one. And thing two is then the design, the construction, and the deployment of a fleet of reactors that are able to do that. Now, there's a big mega trend in the nuclear industry, which you're all familiar with, which relates to small modular reactors. And small modular reactors are reactors that intend to go from an economy of scale to an economy of series, because this could improve economics in principle, and this would limit the financial burden on the nuclear industry. You know, the big projects are very expensive, so also difficult to manage and so on. But the idea here is to have standardized nuclear islands, which you could produce at the same location and then ship around, always the same, with a small footprint, so easy to transport, and also serve a wide range of new applications. For example, powering data centers or powering steel making industries and the like. So just to mention a few examples. Of course, this has to be demonstrated on a wide scale in the industry, but it's a direction, let's say. And the kind of reactor that we intend to deploy is exactly this type. So it's a small modular reactor, but it's also special in the sense that it's not using water as the cooling fluid, and this is what ultimately makes this reactor a fast reactor. So we're not moderating neutrons, and this is what allows us to use depleted uranium as a fuel as well. So we will have fissions of uranium-238 in this kind of reactor. So then the name is becoming AMR, Advanced Modular Reactor, as a subclass of small modular reactors, which could also be cooled by water in principle. Now, in our case, there are certain rearrangements that we have been working on to move from a classical fast reactor, such as a big sodium fast reactor, to pursue this idea of having a small modular system. And the whole idea, again, is to try and simplify things. And so we make some smart rearrangements. For example, by using lead, we can eliminate the utilization of intermediate loops because lead does not react violently with air or water. But there are also some drawbacks with lead. So, for example, it's opaque. You cannot see as you would see underwater. So, in that case, we plan to stick our fuel assemblies outside of the free level of lead, and so other innovations as well. One very important innovation here is to have an integrated steam generator and pump design. So you see the pump is here and it's integrated into a steam generator with flat spiral tubes. So then the flow is also horizontal rather than vertical. And we have the pump, let's say, in the hot collector of the reactor instead of the cold collector. So you see a few differences with respect to classical systems, which ultimately help us achieve this more compact design. Now, as usual, compact designs and pursuing high power increase the power density, and having increasing power density always comes along with some technological challenge, which I'll talk about later on. Now, considering our plan to market, we have a few very important milestones, which I'm showing here. So the first one is related to R&D activities and the installation, commissioning, and subsequent operation of our precursor facility. So this facility is a 10 megawatt non-nuclear reactor, including a turbine. So it's meant to demonstrate the feasibility of operating a full system, including all the components and the coupling with a secondary system as well. Very importantly, this is done at the ENEA's Brasimone Center. There's a very nice video towards the end of the presentation, which I'd like to share, which really gives a feeling of what's happening at Brasimone. So this is one of the key partnerships of newcleo, where we're jointly investing a lot in this location, not just for the precursor, which we will build in 2026 as the key demonstrator, but together with that, a number of other facilities, which I will show later as well. So 2026 date for our precursor, very important milestone. Then we have our MOX production facility in 2030. So this is also a very important milestone, and it's a necessary milestone prior to the operation of our 30 megawatt reactor in 2031, because we need some fuel that has to be produced somewhere. The 30 megawatt reactor will be built in Chinon, so this is decided. It's a site in France, and it's an irradiation machine, essentially. So we miss fast neutron irradiation machines in Europe to perform a wide variety of research developments and test full components in a real system. So that's a key functionality of this reactor, besides being essentially a first nuclear demonstration of newcleo technology. Now, for these two facilities, MOX production and LFR30, we're already engaged in the licensing process. We're in the basic design stage for both, but very soon approaching the detailed design phase as well. And lastly, newcleo intends to have a fleet of commercial reactors of 200 megawatt electric, which will be deployed in 2033 as a first of a kind. So the fleet will be built thereafter, of course. So this is all ongoing, and we're also active with merger and acquisition activities in the meantime to support these developments. Now, coming to these milestones just a little bit more in detail, I mentioned Brasimone as a very important center for lead technology. Later today, I will show a little bit more about capsule and core. These are two facilities for which you see the pictures here, utilized for doing corrosion tests on materials. And I'll also be, just slightly mentioning perhaps the chemistry lab and so that these are facilities where we will do more tests in liquid lead to look at how to handle this coolant, and also what's happening to materials when exposed to stress in this kind of environment, and also a materials lab where we do our own development. So I'll cover these items along my presentation, or what we're doing with these equipment. I won't talk too much about the other facilities, but it's certainly worth mentioning. I mean, some are belonging to ENEA since many years. You might have known these facilities in other contexts. So for example, Chiriche or Nasi. So in these cases, we are testing for heat transfer, thermal hydraulics topics. So we're synergizing with ENEA on those. And we're also building other types of facilities. So for example, Otello, which is a 2 megawatt thermal hydraulics loop where we will test full components such as a fuel assembly, and study a variety of things. So not just thermal hydraulics, but also mechanical vibrations or materials related topics on the real geometry. So not to mention hustle for ultrasonic testing under lead, or handling of the fuel in Manut. So there are really a few facilities. Most are in Brasimone and not everyone. So we have some facilities elsewhere as well. But we're really trying to leverage all the infrastructure that's out there, and Brasimone is at the center of the R&D that we're trying to do. Concerning the MOX production side, I'll just mention essentially that we want to power the first newcleo demonstrator, so the LFR30 machine, and eventually newcleo's fleet of LFR 200s. And that's essentially the main purpose of this facility at the moment. So it's really meant to support a newcleo's development and to go from a first production line of roughly 20 tons per year up to 40 tons. And this could eventually be extended, so depending how the business goes in the future. But that's essentially the purpose. About the LFR 30, as I mentioned before, it's a 30 megawatt machine, at least when it runs at full power. And we will have two phases for this machine. So in the first phase, we will start at low temperature. You see that here. And so low temperature means roughly 400 degrees. And in a second moment, we will move to higher temperature, say 500 degrees. The reason why is mostly connected to materials topic, and I'll get to that later. But the 200 megawatt machine is supposed to run at high temperature to get the most out of that. So that's the commercial unit, and clearly we are happy to get the most electrical megawatts out of this machine for the same investment or cost. So that's clearly the intention. Now, coming to LFR technology, I might not have to explain this in detail, but you know, the use of lead as a coolant has many positive aspects related to the intention to close the nuclear fuel cycle, to achieve high efficiencies, to operate at ambient pressure, and have a very high safety margin. But it also has some drawbacks. So it's opaque, we mentioned that. The melting point is relatively high, so that's something that needs to be managed. It's very dense, and it's also corrosive towards structural steels. Now about the density, I have an old scheme of the G4 forum, so I am happy to see this scheme evolved. Apologies for not having the latest scheme, but the density would cause some issues in this kind of design related to seismic considerations. So this kind of design can be improved and anything moving in the direction of a surface aspect ratio closer to unity is better. And that's what the Japanese colleagues from JAA were trying to do as well in their LB-cooled system. And perhaps also what the Russians are trying to do with their breast system. I'm happy that Mariano was showing a more complete picture of the international background that I'm showing here. Thanks, Mariano, for that. But I'll just take the occasion to mention something very interesting about the breast lead fast reactor, which is it's not a fully integrated pool as we see here, for example, or as we have in the design of newcleo, but you see the steam generators are outside of the primary vessel, which, by the way, is utilizing concrete or a multi-layer of concrete and steel as the material selected. And I guess this is mostly to deal with the seismic topics. So now concerning liquid metal technology, it's not really new. So we all know this technology was first developed by the Russians to power their submarines with lead bismuth, and no LFR was actually constructed beyond that. So we do have, as a broad community, 80 years of cumulative experience with this kind of reactors, but there has been no LFR actually built in Europe so far. And today we have the construction of Brest, which is ongoing in Russia. So here are some timelines. I'm not really sure they are accurate, so please take them with a grain of salt. But it's a very positive news for the LFR community that Russia is actually investing in this technology. And another interesting point is that Russia is active with the rhenium nitride development as the fuel for this reactor, which is also the case for Blikala, by the way. Now, coming to arguably the most important technological issue for lead fast reactors, we have corrosion. So this is a challenge because steel behaves in lead the same as sugar would behave in water, roughly. I'm very bold with this statement. It's not really the case. But the corrosion can be very aggressive depending on the conditions that you're looking at and the steel and so on. So it's a complex problem. And so corrosion can proceed either by dissolution, for example, as we see on the picture on the left, if the oxygen content in the liquid metal is very low. So for a given duration and temperature, low oxygen could lead to this kind of situation. And for high oxygen content, corrosion could take the form of oxidation. And you can see in this kind of chart that the corrosion depth after the same amount of time at the same temperature is much lower. So despite the fact that oxidation is a form of corrosion, it's more controllable in principle than dissolution. And it leads to lower corrosion rates. So the state of the art relies on the utilization of oxygen injected into the system to achieve lower corrosion rates. Now, if you look a little bit more into the details, you can define some stability regions for the oxides that are formed when steels enter in contact with oxygen. And for example, the red line here is displaying the stability line for iron oxides, and the blue line is displaying the stability line for a lead oxide. So if we inject a certain concentration of oxygen into our system, we want this concentration to stay below the stability line of lead oxide because we don't want to form lead oxide to avoid plugging our system, but we also want to stay above the stability line of iron oxide because we want to form these protective oxides. And so if we consider a low temperature in our system and a high temperature, we can define a certain range where we'd like to keep our oxygen concentration. Now, if we increase the temperature in our system, which is what we would hope to do if we want to increase the efficiency of the whole reactor, we may enter a region which is not stable. And then this is not a good idea. So if we only want to rely on oxygen control to avoid the dissolution, that means we should end up with a very narrow oxygen control window. And this can become very, very tough from an engineering standpoint. So not necessarily realistic. So that's a little bit the framework where newcleo starts in 2021. And so starting from the literature, starting from the state of the art, the cumulative experience of Russia and all the 30 years that Europe has been researching lead fast reactor technology, with ENEA taking a very leading role in that endeavor, but also other institutions like SCKCN, Karlsruhe, and other players. That's really our starting point. So what are we planning to do as a company? As I said before, we intend to operate our LFR 30 machine in two phases. A first phase, which has a maximum temperature in the reactor of 480 degrees roughly, and a second phase where we achieve a higher peak temperature. And the reason why we do that is because starting at low temperature gives us a very high confidence that we can build a system keeping corrosion under control, essentially with oxygen injection. So we don't necessarily need to rely on fancy new solutions, but we can rely on the kind of materials that have already been developed in the past, specifically in France, and materials that were utilized for Phoenix and superphoenix sodium fast reactor. Now, of course, materials is a very big word, and you need to look a little bit more into details and into your components to understand what are exactly the needs. So if we look at our reactor and we consider the roof structures, they are not in contact with the lead. So there's essentially very limited R&D needed concerning this type of components, even though there could be some because it's a new system anyhow. But as far as lead is concerned, we don't need to do much. Now, if you look at the reactor vessel and other components which are replaceable, we can still rely on standard steels, 316L for example, but we do need to do R&D. And the reason why is, despite these steels are very well known, we need to show to a regulator that we can utilize these steels in a safe manner and that they are compatible with lead under the specific conditions that we are planning to have in our reactor. with a specific design that we will have. So we do need to do this qualification in lead. And lastly, red color code is where we need extensive R&D. And this applies in general for all components when we move to a higher temperature phase. But already in phase 1, this applies to some components, and specifically to this amphor-shaped inner vessel component number 3 here, because it will be installed from day 1, but it will move from phase 1 to phase 2 without being replaceable. So that means this component already requires some sort of surface modification or the use of a new material already in phase 1. And a similar thing could happen to the steam generator tubes, because these tubes contain heated steam on the inside, or boiling water, and hot lead on the outside. And so far, nickel alloys have been widely used for this kind of component, but liquid lead is very prone to dissolve nickel. So that requires some substantial R&D effort. Now in the phase 2, we will focus on surface modifications and new bulk materials, of course. And this broadly defines 3 R&D programs, which are also coupled with chemistry and irradiations as a key part of the development activities. So how do we combine this strategy with the timelines of newcleo? This is what I'm showing in this slide. The first thing is, of course, we had to lay foundations. So starting as a startup company, we didn't have a team, an infrastructure, internal processes, which are very important as related to quality, partnerships, and so on. So that's really the first thing we've been doing since 2023. September in 2023 is the moment where we started to work on materials, so still relatively young as an organization. In the second phase, once we have labs up and running, we start to screen. So in this phase, we are de-risking technology. We're doing a number of tests and trying out different options, particularly as related to coatings, and also working in parallel on some mock-ups and using all the facilities that I was showing before. In this phase, we also have 2 important milestones. So we will deposit a request of authorization to construct our reactor in France. I didn't mention this before, I believe, but we are very engaged in the licensing phase already since some time, so achieving some good results there so far. And that's an important milestone for 2026. And we will ultimately build up a materials dossier, which we intend to hand over to the regulator in 2030. In the third step, we can start talking about formal qualification of materials, because at that point in time, we will be utilizing our own irradiation machine to test full-scale components in real environments. So with the real geometries, with lead as a coolant, and with the fast neutron flux, which is what we cannot do anywhere else until then. We will then roll out our commercial offering. So by that point in time, we need to have surface solutions or new materials. And eventually, we may as well consider going beyond when it comes to temperatures. So developing new materials, and this is a long process. That developing new materials in nuclear is difficult. So we have to start today. And the consequence for R&D programs is that we have these 3 major programs running in parallel. The first one looking at the qualification of standard steels in liquid lead for the low temperature phase, and the development of coatings and new materials for the longer term to achieve higher temperatures. And it's clear it's a huge effort. It's a very ambitious program, so we cannot do everything at the same time. And that doesn't mean we cannot run programs in parallel. It just means we will allocate our resources with a higher emphasis by order of priority 1, 2, 3. So steels, coatings, and new materials, even if we start today running everything in parallel. So since our birth, we managed to grow a lot. We're over 40 people by now, spread in 4 different locations. So we have Lyon, three locations: Lyon, Brasimone, and Turin. Despite in Turin we have separate labs. Our team in Lyon is mostly focused on materials engineering, so providing the link between the LFR construction project and the R&D needs. The chemistry unit in Brasimone is where we are doing all the environmental testing and handling the chemistry of lead. And then we have these other two units in Turin, metallurgy and characterizations, which are closer to the development of new materials in bulk form or in coatings. And I always like to explain to people, this is a very nice picture of our team taken in Brasimone, but it's not in January, it's rather end of April. So if you ever go there, you should consider having a coat with you. Now about our infrastructure, we have, as I just mentioned, Brasimone and two different locations in Turin, which are focusing on different aspects of what we need. And we are building this infrastructure in close cooperation with ENEA, but also with Istituto Italiano di Tecnologia, with whom we partnered via a public funding scheme called PNNR in Italy. So that's very interesting how public funding schemes can be utilized to accelerate Generation IV deployments. And in this case, it's a very special funding scheme which allows to purchase infrastructure with up to a 50% public funding. So that's what we're doing there. Environment Park is the location for one of the labs, and the other location is a location from Politecnico di Torino. So in Turin, at our characterization lab, we have all these tools here. I won't enter the details, but essentially we are equipping ourselves with the top-notch equipment, latest generation, to be able to go deep into the topics and solve problems. Whereas then also for the metallurgy, we will have some equipment to do casting, heat treatments, transformations, or mechanical tests in air. And then everything that's related to lead is happening in Brasimone at the ENEA side. So corrosion testing in stagnant capsules. We have 18 of these capsules, each one with roughly 1 liter of lead, which can handle temperatures up to 750 degrees with automated oxygen control systems. And similar for our core installation, we have 2 flowing lead loops. One can host 32 samples, the other one can host up to 160 samples, and the first one will be used more for high turnover test and European projects context, while the second one will be mostly utilized for running very long-term tests and generating statistics. In Brasimone, we also have a range of mechanical testing machines, which will include lead testing capsules, such that the mechanical stress can be applied while the samples are exposed to lead environment. And all of this, it's worth mentioning, is work from our group companies, Fucina and SRS, who are designing and constructing these facilities. So that's a great job done by them, also in collaboration with ENEA, thanks to their experience managing all these kind of machines. So now I'd like to share a few highlights of what we've been doing so far in these programs, and just to show that it's not all planning, which is very important and necessary, but we're also getting our hands dirty along the way. So a few highlights, and also to explain a bit more in detail what's inside of these programs I described. So in the first program, we are really looking at standard steel products. And when I say that, I refer to specific geometry, so real products, right? So forged plates, rolled bars, cold worked tubes. And those are the things we actually intend to qualify. And it's very important not to think of materials purely as a given chemistry, but also a given chemistry with a certain heat production, a certain microstructure, a certain manufacturing route, and a given geometrical shape. So those are the elements we intend to work on. And in that sense, we already did a number of tests here. I'm just showing an example where we investigate some transients and so on, different oxygen contents, and so far we managed to reproduce essentially the state of the art, having either oxidation or dissolution depending on the oxygen concentration. So this is work done in collaboration with ENEA and CA. And another very important aspect related to the qualification of standard steels is the standardization in the European context. So lately we've been working heavily in the CN Workstream 64 with AFSAN, but also in ConnectNM European framework project for that matter. I'll say a few words in a moment, but we've been working along with these contexts to standardize or provide, not to standardize, but start with a guideline on how to standardize corrosion tests in heavy liquid metals. And the important thing here is it's not about specifying exactly what parameters should be defined in a given experimental test setup, but it's rather to provide some recommendations. So for example, if you use a certain volume of heavy liquid metal in your test, you want to mention that and explain that and consider implications of that. So just a few obligations for the moment concerning this guideline in RCC MRX Appendix A2 discussions context for 2025 edition, but then again, mostly recommendations. So formally speaking, nobody would really be obliged to use any recommendation coming out of there. Now, in the long term, we would like to have standardization of how to perform this kind of corrosion tests. And that's something the whole community could benefit from. Of course, to do that, it's also very important to have a very thorough understanding of what's the underlying phenomena driving whatever corrosion study one is corrosion phenomena when studying. But this is not simple, and it's not necessarily given in the case of liquid lead. So that's one of the challenges that we face. So at the same time, we work with the European projects context, and we're involved in two project proposals called Robin Hub and Quadisim, and these proposals are related to the development of a test bed and round robin test and the management of databases in a structured way. And the idea is to come up with an indication how things should actually be done to pursue the goal of standardizing everything and eventually have this obligation to respect the standards. So in this case, what I really wanted to mention is that similarly as we're trying to leverage some public funding schemes at national level, also at international level, cooperation is pretty much needed to pull all the players in the same direction and achieve widespread acceptance of these new technologies, without which the actual deployment will be very difficult for all the players for that matter. Now, in the second program, we are looking at surface modifications in a broad sense. And surface modifications is a very broad term as well, and you could think about different possible modifications depending on your component, because there are different sizes and different geometries, different levels of complexity, different underlying materials with their specific microstructural state and manufacturing route. So in the case of vessels, we really think about industrial methods. There's no other workaround because these are large and complex objects with long lead times. And so here we consider techniques such as weld overlay, pack cementation, or spraying, or plating. I mean, these are the standard methods that can be envisioned. For core parts, we need to rely on special processes because many of the parts are cold worked, since that is a good approach to reduce swelling, which we don't like, right? So special processes such as PVD or CVD could be a good solution, or even other routes such as laser cladding. That's something other players are working on, or similar. And lastly, out of core components with, say, medium size but still high complexity, one could think about still some industrial techniques like plating or pack cementation or the like. So here I just want to show one possible example, a highlight of a PhD thesis work that Politecnico di Milano is carrying out, where we investigated PVD of a variety of compositions, but compositions rich in aluminum because this is known to perform well in lead. And so we developed this technique. We managed to control the morphologies, and we ran some ion irradiation tests and some corrosion tests. And what you find with these kind of coatings is that the irradiation is inducing some segregations, but despite of that, we still see a good behavior in the corrosion test that we performed under screening conditions, so 600 degrees, 10 to the -7 oxygen content, which was a positive surprise, say, in spite of these segregates that ion irradiation is inducing. So a promising route to explore in the context of a PhD thesis. Concerning new bulk materials, we have different pillars which we are investigating. The first one is related to corrosion-resistant austenitic steel. So here the idea again is to add aluminum or silicon as alloying elements to the steels because these elements are able to form very stable and protective oxide layers. Then we have a second pillar on ferritic steels. Ferritic steels are very interesting because they do not swell, and generally, at least in lead bismuth, they have been considered to be prone to liquid metal embrittlement. This is not so strong an effect in liquid lead. Nevertheless, it remains kind of the key research direction one can take if one is working on ferritic steels. In general, their corrosion behavior is a bit better, but one needs to be careful about the embrittlement part. One could envision advanced materials as well. This is something we're definitely interested in because some advanced materials have very good corrosion behavior. And here I would imagine high entropy alloys, silicon carbide composites, ODS steels, max phases, refractory alloys, you name it. It's all very interesting. It's just perhaps for newcleo, the timeline is not so compatible with our own milestones. And so again, the European context can provide a lot of support here. And we're happy to be involved as the key users of future technologies that may come out of research. And lastly, advanced manufacturing. It could either be additive manufacturing, but not just additive manufacturing, which is also potentially very important. We have a number of activities here, including a PhD thesis, but also some collaborations with the additive manufacturing and materials engineering group of Generation IV Forum. So where we have Isabella Van Roy, and which I'd like to thank, and where we are also active as an invited observer. So that's also a context worth mentioning where international cooperation can support the development of advanced G4 technologies. A highlight of our work here has been the development of our in-house alumina forming austenitic steel, where we did some tests so far related to corrosion, achieving good results with no corrosion displayed, and with some simulations of manufacturing steps using a Gleibel machine, so to simulate forging and obtain some initial indications on how to manufacture real products. Now, new materials are hard to use because the route to qualify them is steep, and that's something I mentioned before. But I think the longest step is related to irradiation, long-term corrosion, creep testing, and aging. And very often one is asked to test these properties up to 1/3 of the product life. So if you consider a vessel which has to stay there for, say, 60 years, then you need to provide some test results for 20 years. And that's already saying a lot. But in general, we still believe this is something that could help new technologies perform at their best, and so we really invest in this as well. So now coming to a conclusion and some challenges that lay ahead of us. I've talked a bit about newcleo's project, which involves the MOX manufacturing part and the LFR technology. Corrosion as a key challenge for LFR technology, and oxygen control as the state of the art to keep corrosion under control. Our own material strategy with diversification as the key element to pursue high temperatures. So we have steels, coatings, new materials, and I showed how our strategy is fitting into the broader picture of our company's milestones, and then I provided some highlights of the R&D programs. Now, some challenges that lay ahead of us are certainly related to the technology itself. So we don't have fast reactors in Europe to develop in-pile experimental programs, and ideally for any player trying to develop new reactor technology, that's where most of our investments should go into, actually, because that's where we will find out things we don't know or which we cannot simulate so easily. Of course, we can do many irradiations with ions, and that's something we'd like to do. But you're certainly all aware of the eternal debate of equivalence between ions and neutrons irradiations. And again, I'd like to mention maybe that's something where international cooperation can do its thing. Recently, I've attended the SMINS workshop organized by OECD, ENEA, in Madrid, and there were very interesting presentations coming from the US colleagues on how to provide these correlations, and I know we're doing a lot of work on that in Europe as well, but also in other parts of the world. So that's something to consider. Then standardization and the regulatory framework, for sure. I mean, this is also related to our own milestone and scheduling. And very often there aren't any regulations concerning these new technologies. But having an initial starting point is very important. So early engagement with regulators and the broad community around the development of these technologies is very important. Last but not least, supply chains and financing schemes. But supply chains specifically, we intend to rely on some materials that are known, but which may have not been produced over the last decades because these reactors that we're intending to build haven't been built lately. And so restarting supply chains of old materials which were very well known can take some time, or developing the supply chain for new materials developed is also something that can take some time. Of course, related to the financing, this is an important piece for any new company trying to develop a new product which is still not in the market and is still not acting as a source of revenues. But here come again some strategic interest of the countries involved in such development. So for the time being, we do see good news coming from the European context with at least as far as materials are concerned. So we're trying to leverage on the European funding schemes available, both at the national level and at international level. So with that, I'd like to close with a short video and hope you all enjoy it. Okay, so thank you very much. I hope you enjoyed the video as well. Wrapping up a little bit of content that I've been discussing earlier. So with that, I'd like to close. And of course, open for any questions there may be. So good. It was good to see you in the video as well, Mariana. So, yeah.
Okay, thank you so much, Francisco. Very interesting presentation. We have time for some question. I see some question from the questions on function on the chat, so I will go there. But let me start from my side because we are working together. But I would like that we highlight to all the participants discussion that we have several times. So my first question for you, Francisco, do you see any showstopper for the LFR development concerning the material? What is your main concern in developing materials for LFR for short term, medium term, long term?
Yeah. Thanks, Mariana, for that question. And indeed, we have many discussions around this topic,
Yeah,
and we get passionate about it. Look, I think if we look at the short term, the main concern is just putting order into all the knowledge that has been accumulated. And unfortunately, I mean, both fortunately and unfortunately, fortunately, there has been really a lot of stuff done. Especially in Europe in the last 30 years, in a research context. And fortunately, because the research context is very good for understanding things. So if you take a snapshot today and a snapshot 30 years ago, when you compare the level of understanding, it's very clear we have improved so much. Unfortunately, this was a research-oriented context, and I say unfortunately because maybe all the information has not always been gathered systematically or reported systematically for that matter in a way that we could, take and use readily. So right now, my main concern is to take all the learnings that are available and that are ready usable in the context of an industrial company that wants to put a product out in the market, going through a licensing phase, and then take the gaps which need to be closed and close those gaps. But you see, it's really more a matter of form, how we are doing that, rather than a matter of substance. And this is also related to all the knowledge that you have accumulated in ENEA as well. So the likelihood we can keep things under control at low temperature in the short term is very high. So that's not just a gut feeling, it's also based on evidence. The only thing is we really need to produce information systematically, being able to track, all the boring part for that matter for researchers, but which is very important for engineers. So calibrations and so on, and keep track of decisions and all of that. So that's for the short term. In the mid to long term, we really need to go to the high temperatures. And well, let's say nobody has ever built a reactor which is able to operate at very high temperature in liquid lead for a long time. So there comes higher technology risk, but there are very good solutions also. And we're also studying them systematically. So I'm also very confident we can do that. And there's plenty of literature showing that there are very good solutions to achieve that. And then the challenge becomes how to convince, a regulator that these solutions are safe and sustainable from a technical perspective. To achieve that, the radiations are a very important piece of the puzzle. And so if you ask me if I have one main concern, I'm more concerned about irradiations than anything else. Why? Because these are the wild card. So they can turn the table around and that's where we may find some unexpected things. But overall, my level of confidence is high. Okay, I'm an optimistic guy, but we're doing a lot of systematic work to do things in a proper way, and so far results are good. I mean, we've had a very positive year and a half. And so I'm as confident as I was a year and a half ago for now. Yeah.
And from your side, do you see any role for the GIF community for supporting, for example, the radiation stuff? Because in Europe we don't have we have a radiation machine, but not fast spectrum irradiation machine. So do you see any role for the GIF in supporting this irradiation concern worldwide?
That would be very nice. I'm not so well versed in the institutional part yet to give a clear answer. Probably you're better positioned than I am to make a statement there. Let's say,
So let's say this way, Francisco, what you can do for you to support this?
yeah, right. I mean, look, if you look realistically at the options that a company like Newcleo would have today to access irradiation facilities, there are not so many options of interest for us. So we're looking at fast reactors. And any fast reactor which is somehow close to the Generation IV community would be a good opportunity to discuss. We have ongoing discussions with the Japanese colleagues, and so that's a thing, and we're already doing that. But of course, United States maybe have options, Russia maybe has options, and if I only think about the technology, Generation 4 could be a good context to have all these discussions, regardless of whatever other situation, which may make things a bit more difficult. But technical needs should be a driving force for this kind of developments. Otherwise, if we don't join forces, I find it very hard to believe we can make it as a fast reactor or Generation 4 reactor technology. So coming to your question, if you have ideas on how to facilitate access to faster radiation machines out there, that's certainly welcome. Besides that, again, I stress the point, there are some working groups where we're already present. We see what's happening, and I know Generation 4 Forum is doing a good job. And I mentioned the specific case of the additive manufacturing group, and that's where we have quite a few exchanges and mutual learnings and discussions on how to standardize things or how to approach qualification of additively manufactured parts. And that is very relevant, not just for us potentially, but also for other developers. And I think that kind of context is bringing value. Um, it's um, it's a narrow scope, but it's still an important scope. So I'm pretty sure there are more of those working groups. That's just the one I'm aware of, but those kind of activities are valuable to my eyes. So.
Very last question from my side before moving on question and answer section from the chat. You mentioned additive manufacturing. Do you see that this new technique for manufacturing will play a relevant role in the short term, or they will come for medium and long term for the technology?
I think this is very much design dependent, frankly. So, in the short term, now I put my Newcleo hat on and I will say something a bit bold, but in the short term, I believe relying on well-known methods, including well-known manufacturing methods, could make things easier from a regulatory perspective. But this doesn't necessarily mean that's the optimized technical solution nor the best solution. Additive manufacturing has some advantages, depending also on the technique, the specific technique you're considering. So certainly freedom of design, and if freedom of design is something very important for your specific design, then it can be a real enabler. Also reduction of lead times in some specific cases, and that can be a very important aspect, often overlooked or underestimated, because some components are very long lead time, and this is not always compatible with the funding schemes that some startups rely on. And so from that perspective, it could be a game changer even. Take the examples of some vessels. So when you talk about vessels, you talk about big forged components. And then you need to look at your financial aspects and see if you're well covered. Yeah, so in some cases, also you could benefit from some specific performances which you could obtain from additively manufactured materials. So I think it's um, it's a very interesting development, probably not the most useful for newcleo in the very short term, but it could unlock some opportunities, and it's not given it could not be useful in the short term, depending on your own scheduling. Um, but that's very design dependent and situation dependent on the company for that matter. But I think it's beyond doubt that in some cases, additive manufacturing will start to be adopted. And I know there are some companies out there working on different technologies than ours that are relying on additive for producing some components. And there are benefits that you can take, maybe some performance improvements as well. So, for example, improving flow patterns in at the entry point of fuel assemblies could be a thing if you work on the lower foot. Some companies try to commercialize this kind of product. So I think it's super interesting actually, and even irradiation performances could be improved given the very specific microstructures you could achieve with this manufacturing route.
Okay, let's on the question that I see on the chat from the audience. One of the first was, thank you for your nice presentation. Is it correct to assume that to construct and operate a LFRs 30 phase 1, newcleo will mainly use already qualified material or merely qualified materials, no coating, for example?
I'm not sure if I'm getting the point of the question, what is correct or what is not correct. I think what we are trying to do is understand exactly in the conditions that we foresee for our reactor. So specific flow patterns, specific speed, specific temperature, oxygen content, specific foreseen incidental and accidental or possible accidental scenarios. Derive a qualification scheme for the steels that are already known, test them, and show that things are okay. Now, this is a plan, and we are confident this plan can work. It doesn't mean it will exactly work like that, or that we will not have to make adaptations along the way or redefine our initial corrosion allowances based on what we find. So it is R&D, and not everything is fixed on stone yet. So I don't know if this is answering the question, Mariano, in your view, but um, let's say the literature so far has done extensive experiments on these kind of steel. So I'm talking about 316L, 1515 titanium. Their behavior is pretty well known. To be fair, it's much more known in lead bismuth eutectic than it is in lead. But the good news for us is lead is less aggressive than less bismuth eutectic for what we know from literature and from what we see in practice. And this increases our level of confidence as well. Um, but it is also true that we need to perform all the tests in a very systematic way, keeping trace of many things. And doing that, maybe we learn. So,
Yeah, and as you said already, there are many data in Europe, mostly on lead bismuth, you're right, but now we're moving on to get the data in lead. But I guess from the short term on proven material, I guess the main effort will be on adapt codes and standards for design rules. So this will be
correct.
one of the most challenging for the time schedule, I would say, not for sure. It is not a showstopper, but there is a lot of work to do.
It's a lot of work. And I think the question was asking also, why not code things as well? Well,
Yeah,
again, so it's fair to point out, in the worst case, it could happen. We say, oh, well, we don't feel really comfortable with our own design criteria, so we would be happier to have some coating. I cannot exclude that today. It's not the intention, and based on the data that we have today, we conclude we don't need that. This could change if we find some surprises. I don't think so, But if that is the case, well, we will adapt, and that's also why we have these programs running in parallel. We don't want to arrive to that situation without having a plan B. So it's an option. We're developing coatings in the meantime as well, and certainly having coatings would reduce the corrosion rate even further, even at low temperatures. So there could be a benefit in that regard. But let's say it's not the plan. We don't consider it's a mandatory requirement at the moment. Maybe let's call it a could have requirement or a nice to have requirement.
Yeah, that's good. Yeah, that's good. Okay, another interesting question from the audience. Which would you consider a bigger roadblock to making progress on deployment of nuclear technology? The physical issues of the technology, engineering and the R&D issue, the lack of EU nuclear policy, or the supply chain?
I would not see the technology itself as the main thing. I am a technology guy, and I trust a man can do many powerful things, provided, so that that's the tricky point, there's sufficient focus and financial support. I mean, just think about it. We came up with a travel to the moon, for that matter. How complex that was at the time, I think as complex or perhaps really more than building this kind of technology. So I have no doubts that with sufficient focus, financial support, and dedicated effort, we can build these technologies. Also, it's not like they have never been built. So we have operated sodium fast reactors in Europe in the past. There are sodium fast reactors out there. There have been lead fast reactors, and we have also gathered some learnings. So level of confidence in that regard is high. Supply chain is really, again, a commercial issue. So this is kind of linked with the financial schemes, and so there has to be good business behind that. What I see, matter of fact, is there's very broad interest, commercially speaking, worldwide on small modular reactor technology, and very high willingness even of steel makers, for which the volumes maybe are just a far promise, but a high willingness to support us. So I'm confident also the supply chains could be worked around. Maybe there are some very critical items, niche items. This is also entering some strategic geopolitical discussions in some very specific cases, but it should be considered as well. So there could be some hidden issues there to consider. It could be easy to overlook those issues. So that certainly is an important challenge. And regulatory framework is similar in a sense. I'm sure there are many challenges there. We are doing early engagements with the regulators, trying to bring regulators into the game early on, not just talking to the industry, but also talking amongst themselves, because, you know, if you like to standardize a product and put it out in different countries, but each country has different regulations which would then affect the design, this is really a big challenge for small modular technology. So perhaps if I had this one, I could think about this last item as maybe the most difficult one. But also the supply chains may hide some challenges for us there. Good news is there's really broad interest, really broad excitement across all the type of players, and also a very thorough understanding of the fact that nuclear technology is pretty much needed to help us achieve our clean energy targets and support the energy transition. So I do feel a widespread willingness to support, and this keeps me hopeful.
Well, it's another question that I don't know if I will be not able to answer, so I will forward to you. They are asking if Germany has apparently committed to no longer opposing nuclear energy at EU level. Do you think this will affect Newcleo in any way? So maybe this will speed up your program, or will have no effect on you? What do you think about this new scenario in Germany?
I mean, newcleo is interested to commercialize a fleet of lead fast reactors in Europe. So any country that's willing and open to embrace this kind of technology, we're more than happy to talk. And so the commercial aspects must still be developed. At the moment, the newcleo is focusing on France, UK, Slovakia, and Italy. Italy's a non-nuclear country yet, but things are changing in Italy as well. And we are certainly ready to support any transition that countries may wish to pursue. Similar considerations could be made in the case of Denmark, for example. So these are, of course, country specific and related to country policies. At the moment, we need to focus on a couple of strategic countries, but our intention is to deploy this fleet in Europe. And so, welcome Germany to the nuclear again. Yeah.
Yeah, and my feeling is that just in case Germany will back and considering a nuclear option, in Europe, the most relevant country from an economical point of view are France, Germany, Italy. So if these countries are working on it, most probably we will be able to push on nuclear much better than what we've done so far. But this is just my feeling. But I would be very happy if Germany back on nuclear. Would be very happy.
Yeah, absolutely. And by the way, Germany has done a lot of work on heavy liquid metals, which via their institution.
Yeah.
So
They have a big experience. Yes, indeed.
would be
And
very
very last question, still from the audience. It's about your planning for the commercialization. What is the planned build time for the FOC LFRs 200? I noticed that there is only 2 years planned between the 30 megawatt prototype and the 200 megawatt reactor. This seems like a short amount of time to allow for any design change learned from the 30 megawatt build.
correct. Yes, we are progressing the designs of these reactors in parallel. So we are not doing the design effort in series. And the main underlying idea is that we can transpose any technological development we're doing for the 30 to the 200. Certainly, I can tell you from a materials perspective, nothing will change if you're producing 30 megawatt or 200 megawatt, as long as you stay in the same temperature range, flow conditions, and so on and so forth. So from a materials perspective, we don't see a big difference on that. From a commercial perspective, it's important to run these initiatives in parallel because the 30 is not the commercial product that will allow newcleo to be a sustainable business in the long term. That's rather the 200 megawatt offering. And the idea is to start with the first of a kind, which ideally would start immediately operating at low temperature, at high temperature, sorry. But the possibility of starting perhaps at a lower temperature for some prudential time is also a possibility. Our current planning is that in 2033 we will construct this reactor, which we are already designing in parallel.
Oh, there are no other questions from the audience. Francisco, let me thank you once again. It was very interesting, your presentation. It was very interesting also this final discussion with you. Thank you so much for supporting our GIF initiative. And for all the participants, let me recall that this presentation, this discussion has been recorded, so you can soon find it on our website. And please do not miss the next one, that is the 7th of July, with the Black Alla, still on the LFR, with a different topic. We'll talk about fuel, but will be very interesting. So thank you, Francisco. Thank you, everyone, and enjoy the rest of the day. Thank you so much.
Thanks, Mariano. Goodbye, everyone. Thanks for joining.